In this chapter, we'll cover the chemistry of aromatic compounds. The reason why aromatic compounds were named as aromatic is because some of the initial aromatic compounds that were discovered had an aroma associated with them. For example, vanillin, it results in the smell associated with vanilla. Methyl salicylate is wintergreen oil, and there are other examples. TNT, or 2,4,6-trinitrotoluene, is an aromatic compound that contains 3 nitro groups and a toluene molecule. Many aromatic compounds are sourced from coal and other petroleum products. For example, benzene, toluene, which has a methyl group on benzene, xylene, which has 2 methyl groups, indene, which is a 5-member ring fused to benzene, naphthalene, biphenyl, anthracene, and phenanthracene are examples of aromatic compounds that are isolated from coal and petroleum. In order to learn the rules about naming aromatic compounds, it's a good idea to learn some basic parent names in aromatic naming. For example, benzene is a 6-member ring that contains alternating double and single bonds. Aniline has an NH2 group attached to benzene. Phenol has a hydroxyl group on benzene. Toluene has a methyl group on benzene. Benzaldehyde is an aldehyde attached to benzene. Benzoic acid has a carboxylic acid on benzene. And then finally, anisole has a methoxy group on benzene. In order to name substituted aromatic compounds, we simply use one of these parent names and add a substituent based on where they're located in the benzene ring. We can use numbers as we have for other alkyl compounds, or we can use ortho, meta, and para if there are 2 substituents on a benzene compound. For tri-substituted aromatic compounds and those containing more substituents, we always have to use numbers rather than ortho, meta, para. In other words, ortho, meta, para is used exclusively for naming disubstituted aromatic compounds. Here's a few examples of aromatic compounds and how we would name them. The first example has a benzene ring, which is our parent name, and it has a bromo substituent on it, so this compound is named as bromobenzene. The next example has a nitro group, and it has benzene, so this is a nitrobenzene compound. And then the last example is propylbenzene, since it has a propyl group attached to benzene. Occasionally, we might need to give the benzene group as a substituent on a more complicated compound. This occurs often when we have an alkyl group that is at least 7 carbons or more, or we have a perhaps shorter carbon chain that has another functional group that is higher priority than the benzene ring. In those cases, we use the substituent name phenyl for the benzene. As an example, here we have a 7-carbon chain with a benzene attached on the 2nd carbon, so this is named as 2-phenylheptane. Note that the phenyl group is not the same as a benzyl group. They're often confused by students. A benzyl group has a CH2 group and then a benzene ring. Let's cover a few examples of disubstituted benzene compounds. First example has 2 chloral substituents on benzene, so this compound is named as 1,2-dichlorobenzene, or we could use ortho-dichlorobenzene. The next example has two methyl groups on benzene. So this can be named as 1,3-dimethylbenzene, or it could be named as meta-dimethylbenzene, or we could use the letter M in front of dimethylbenzene to indicate that this is a meta-substituted compound. Note that we could use the letter O for ortho or P for para as well. The last example for the disubstituted compounds has a chlorine on the fourth carbon from the aldehyde. So this can be named as 4-chlorobenzaldehyde or para-chlorobenzaldehyde or p-chlorobenzaldehyde. Here's a few examples of tri-substituted benzene compounds and those containing more substituents. The first example has two methyl groups and a bromine on benzene. So alphabetizing these substituents, we would name this as 4-bromo 1,2-dimethylbenzene. We name the two methyl groups on carbon 1 and 2 since they're right next to each other. And then continuing in the direction of the bromine, at least the shortest route to it, to give the bromine on carbon 4. Any other possible numbering method would give or will lead to higher numbers for the location of these substituents. The next example has a hydroxyl group on benzene, so this is named as a phenol, and it has two methyl groups on the phenol. One is right next to where the hydroxyl group on carbon 2, and then the other one is on carbon 5, so this is named as 2,5-dimethylphenol. The last example on this slide has three nitro groups on a benzene that has a methyl group. You might recall that such compounds would be named as toluene, and since we have three nitro groups, this would be 2,4,6-trinitrotoluene. In this question, we're going to try to provide the name, the IUPAC name for the following compound, which contains a benzene ring, an ethyl group, and then two nitro groups. Parent name for this compound is benzene, and it has two different substituents, an ethyl and a nitro group. We alphabetize those two types of groups, so ethyl goes first, and that would be on carbon 1. The reason for that is we have a nitro group next to it, so numbering this carbon with the ethyl group would give the lowest possible numbers we could use for locating the substituents. So this compound would be named as 1-ethyl, 2,4, so continuing in the direction of these nitro groups would give this carbon 2, and then this one 4, so 2,4-dinitrobenzene. Let's now discuss the structure of benzene and what is special about benzene. Benzene is a compound that contains a ring with 6 carbons that are joined together by alternating double and single bonds. There are two resonance structures for benzene that we can get from moving these pi electrons around the ring. On the left, we see that there is a double bond between these carbons, but if we move those electrons here, we would create now a double bond between these two carbons. That would force every other double bond to move to the left in a clockwise fashion to create this second resonance form. In these structures, we have a bond that in reality is not a single bond or a double bond. Is actually a bond and a half when we average out the two resonance forms of benzene. The true structure of benzene can be thought of as looking something like this, where there is partial double bond character in between every single carbon-carbon bond. Each carbon is sp2 hybridized in benzene and has a p orbital that forms a pi cloud that is both above and below the plane of the benzene ring. This is illustrated here, where the p orbitals are adjacent to each other on each carbon, and the top lobe on each p orbital will overlap so that there is a pi cloud here on the top of the benzene ring, but there is also a pi cloud underneath of the benzene ring. Experimental evidence has shown that the carbon-carbon bonds in benzene are about the same bond length. They are approximately 139 picometers, which is somewhere in between a typical length for a single bond and a double bond between carbons. The electron density in all carbon-carbon bonds is also identical, as well as the bond angles, which is about 120 degrees between the bonds between the carbons and also the hydrogens that are attached to these carbons. Hydrogenation experiments involving alkenes and dienes and aromatic compounds have shown the relative stability of these compounds. For example, cyclohexene, if treated with hydrogen gas and a metal such as palladium, would be hydrogenated and converted into cyclohexane. So in other words, palladium adds hydrogen atoms to this double bond to convert it into an alkane. The reaction leads to the release of 118 kilojoules per mole, since the reaction is exothermic. If we do a similar experiment with cyclohexadiene, adding hydrogen gas and palladium, the double bonds in this diene will be converted into single bonds, and therefore we will have cyclohexane. Based on the experiment from cyclohexene, we could theorize that the reduction of the double bonds in one cyclohexadiene should release about 236 kilojoules per mole. In other words, if we double this value, which is the release, the energy release from the hydrogenation of a single bond, we should be able to approximate how much energy should be released from the hydrogenation of two double bonds in this diene. When we do this experiment, we have found that the reaction actually leads to only 230 kilojoules per mole of energy being released. Since the product in both reactions, the reduction of this diene and this alkene, both lead to making cyclohexane, the difference in energy between these two reactions is based on the fact that a 1,3-diene has a small amount of stability due to the conjugated double bonds. In other words, we have found from this experiment and others that when we have a double bond that is alternating with a single bond and then another double bond, those two conjugated double bonds tend to be more stable than individual single bonds. And for this particular example, that stability is somewhere around 6 kilojoules per mole. This extra stability from conjugated double bonds leads to benzene having a stability of about 150 kilojoules per mole more than you would expect. So in other words, when we try to hydrogenate benzene, so in other words, add hydrogen gas and palladium to convert it into cyclohexane, based on the experiment we saw with cyclohexene being converted into cyclohexane, you would think that if we took this value and multiplied it times 3, since there are 3 double bonds in benzene, we should theoretically release from the reduction of benzene into cyclohexene about 356 kilojoules per mole, just simply by taking 118 and multiplying it by 3. However, when this experiment is run, we find that the reaction only releases about 206 kilojoules per mole. The difference between the actual amount of energy released and the expected from tripling this value here is due to not only the conjugation between these double bonds, but also something else. Clearly, we can see from the example of this diene that having conjugated double bonds adds a little bit of stability to the compound. But that was only about 6 kilojoules per mole. In the case of benzene, we see a huge amount of stability, and this is due to something that scientists like to refer to as aromaticity. So in benzene and other similar aromatic compounds, there is something special about them in terms of stability that leads to a very strong and stable ring. In the case of benzene, it's approximately 150 kilojoules per mole. Just learned aromatic compounds are extremely stable molecules compared to most other types of compounds. There's also other compounds called anti-aromatic compounds. These are the exact opposite of aromatic compounds. These are compounds that are extremely unstable. And then somewhere in between are the non-aromatic compounds. These are your typical or basically 99% of organic molecules. They're neither anti-aromatic or aromatic. There are some basic rules that we have in order to predict whether a compound based on its structure will be aromatic, anti-aromatic, or non-aromatic. The first rule is we're going to name it as Rule 1. This is that in order for a compound to be aromatic or anti-aromatic, it has to follow this rule. And the rule is that molecules must have an uninterrupted cyclic pi cloud of electrons. In order to do this, a molecule must be flat, it must be cyclic, and it has to have a p orbital at every atom of the ring. The second rule that a compound must follow in order to be aromatic is also sometimes called the Huckel rule, is that it has to have 4n plus 2 pi number of electrons, where n is an integer. For example, if a compound has 6 pi electrons, it could be aromatic as long as it also follows Rule 1. Anti-aromatic compounds will typically follow Rule 1, but do not follow Huckel's rule. So they instead have 4n pi number of electrons. For example, a compound that has 4 or 8 pi electrons and also follows Rule 1 would be anti-aromatic. Non-aromatic compounds will either not follow Rule 1, or if they do follow Rule 1, they're not going to follow Rule 2 or the anti-aromatic version of that rule. We're now going to apply the aromaticity rules to determine whether compounds based on their structures will be aromatic, anti-aromatic, or non-aromatic. We'll start with the monocyclic hydrocarbons, which are often called annulenes. The simplest example, or one of the simplest examples, is cyclobutadiene, which has the following structure. Notice it has 2 double bonds, and as a result, it has 4 pi electrons. Each carbon in this cyclobutadiene is sp2 hybridized, so that means that it has a p orbital at every carbon atom. So based on the small size of the ring, this molecule would be flat. Obviously, it's cyclic. As we mentioned, it has a p orbital at every atom, so it has an uninterrupted pi cloud, which means that this compound follows Rule 1 from the aromaticity rules. Now, because it has 4 pi electrons, it doesn't follow Huckel's rule. Instead, it follows the rules based on anti-aromaticity. So this compound would be predicted to be anti-aromatic. That means that this compound is very unstable, and it should come to no surprise that the compound is so unstable that it actually reacts with itself through a reaction called a Diels-Alder reaction, where the molecule dimerizes and it makes this dimer shown here. As we discussed previously, benzene is an aromatic compound, but let's see, based on the aromaticity rules, why that is. First of all, benzene is a cyclic molecule. It has an sp2 carbon, as you can see by the double bonds at every carbon in the ring. That means there's a p orbital at every one of these carbons. The molecule is flat as well because of the sp2 hybridization of each carbon, which would force each carbon to be trigonoplanar. And so overall, the ring itself would be a flat ring. That means that this compound follows rule 1 of the aromaticity rules, in that it has an uninterrupted pi cloud. It also follows rule 2, or the Huckel rule, because it has 6 pi electrons. So you might recall that the Huckel rule says that if a compound has 4n plus 2 pi number of electrons, then it would be aromatic as long as it follows rule 1 as well. So in the case of benzene, we have 6 pi electrons, which is an example of a compound that follow Huckel's rule. So if we plug in 1 for n in this formula, we can come up with 6 pi electrons. So that's an acceptable number for an aromatic compound. Cyclooctatetraene, which is shown here, is a compound that has an sp2 carbon at every atom in the ring because of the double bonds. That means there's a p orbital at every atom. The molecule has 4 double bonds, so as a result, it has 8 pi electrons. So based on the rules of aromaticity, this compound would be predicted to be anti-aromatic based on these rules. Now, that's only true if this compound was flat as well. So that's a requirement to have an uninterrupted pi cloud. However, because of the relatively large size of the ring, this compound is actually able to take on a non-flat shape, essentially a tub shape, which is shown here, where the sides face up or towards the same direction, which means that the ring itself is not a flat ring. By taking on this non-flat shape, the molecule avoids being anti-aromatic. And as a result, this compound is considered a non-aromatic compound just simply because of its shape. This next compound is 10-aniline, or if you want to use the IUPAC naming system, is cyclodecapentaene. It has 5 double bonds. If this molecule were flat, it would have an uninterrupted pi cloud. And then based on Huckel's rule, we can note that this compound does follow Huckel's rule as well. So if we plug in 2 for the Huckel rule, we can get 10 pi electrons as an acceptable number for an aromatic compound, which this compound does have 10 pi electrons. So this compound would be predicted to be aromatic if it were a flat compound. In reality, though, there are 2 internal hydrogens, which are highlighted here, that are generally facing towards each other to the point that they have a steric interaction across the ring. And so that forces the molecule to take on a non-flat shape, which means this compound in reality is non-aromatic. Interesting example of an aromatic compound is methylene cyclopropene. This is a compound that when you look at it, you'll notice that it is made up solely of carbon and hydrogens. So it's a hydrocarbon. Most hydrocarbons typically have very little dipole moment. So in other words, they're very nonpolar. So their dipole moments usually tends to be around 0 dBs. However, this particular compound, methylene cyclopropene, has a fairly large dipole moment, somewhere around 1.9 dBs. The reason for this has to do with a resonance form, as you'll see in a moment, that is highly polar. The resonance form that is shown first above involves a ring that has a double bond, which of course has 2 pi electrons, and then it also has a carbon that has a double bond, but the double bond is sticking out of the ring. So as far as the number of pi electrons within the ring, there's only 3 pi electrons, so 2 from the double bond, 1 from the double bond that is partially on the ring. So the carbon that is part of that double bond has 1 pi electron. So in total, there are 3 pi electrons in this ring. Based on the ring, it is a fairly small ring. It is flat, and therefore it has an uninterrupted pi cloud. So this compound or this structure follows rule 1 of the aromaticity rules. However, it doesn't follow rule 2. So it has an odd number of electrons. So that means that this compound is neither aromatic or anti-aromatic. It is a non-aromatic compound. Methylene cyclopropene has another resonance structure, which we can draw by moving these electrons from this double bond out towards the carbon, the CH2. That gives it a negative charge on that carbon, and it leaves behind a positive charge on the carbon that was part of the ring of that previous double bond. A carbocation that forms here, you might recall, is an empty p orbital. In other words, there's a p orbital there. The carbon is sp2 hybridized. The p orbital has no electrons, but it allows the pi cloud around this ring to be uninterrupted. So there are p orbitals at the 2 carbons that are part of the double bond. Each one has an electron, so for a total of 2 electrons. On this carbon, where the carbocation is, there's also a p orbital, so that allows an uninterrupted pi cloud around the ring. But because there's no electrons there, we have a total of 2 pi electrons overall in this ring. If we go back to Huckel's rule, which has 4n plus 2 number of pi electrons, that's an acceptable number of electrons for an aromatic compound. If we plug in 0 for that formula, an acceptable number of pi electrons is actually 2. So 4 times 0 plus 2 would be 2. So 2 pi electrons would make this compound aromatic, since it also follows rule 1. So since this resonance structure, although is an odd structure because of the charges, since it is aromatic, it is a large contributing factor to the overall structure of methylene cyclopropene. And this explains why this polarized resonance form leads to a very large dipole moment for methylene cyclopropene. Let's take a look now at how aromaticity rules apply to ionic hydrocarbons. For example, if we take a look at 1,3-cyclopentadiene, we'll notice that this carbon here is not sp2 hybridized, and so this compound itself would be considered a non-aromatic compound, since it has an interrupted pi cloud. So there is no p orbital on this carbon to allow the electrons, the pi electrons, to flow around the ring. However, if we add a base, we could remove one of these hydrogens, theoretically, to create this anion shown here. That lone pair uh, would allow this compound to now be aromatic, since we already have 4 pi electrons from the double bonds, the 2 double bonds that we have here. And so if we can somehow get another 2 pi electrons, we can make this ring aromatic. And so what happens with this compound is that this carbon will be sp2 hybridized. It will have a p orbital, and that p orbital will have the lone pair on it to allow the completion of the cyclic pi cloud and allow this compound to be aromatic. So as you'll see in a moment, with the next few examples we'll look at in this chapter, very often when you have a lone pair, that lone pair can contribute to the compound completing the pi cloud and also be counted in the pi electrons in the pi cloud. Or if it's not beneficial towards the compound, in other words, if it's not going to allow the compound to be aromatic, or maybe if it's going to make the compound anti-aromatic, the lone pair instead of being in a p orbital, will be usually in an sp2 orbital perpendicular to the pi cloud of the ring, and therefore it won't count towards the electrons that are part of the pi cloud. Another possibility with cyclopentadiene is if the compound loses a hydride, in other words, an H minus, to produce this cation shown here. It has a carbocation on this carbon, and as we discussed before, carbocations are sp2 hybridized. That means that there is a p orbital that is empty on this carbon, since it is a carbocation. So there are 0 pi electrons on this carbon, and there's another 4 from the double bonds. So overall, there are 4 pi electrons in this compound. And this ring would be predicted to be anti-aromatic. The last example with cyclopentadiene is if the compound lost a hydrogen and left behind a radical, an electron, that is unpaired. That would create this cyclopentadienyl radical. That electron would be counted as part of the pi cloud to give this compound a total of 5 pi electrons. And so this compound is considered a non-aromatic compound since there are an odd number of pi electrons. One last thing that I want to point out with cyclopentadiene, going back to the reaction with base, is that cyclopentadiene is extremely acidic for a hydrocarbon. So most hydrocarbons are fairly non-acidic, so their pKa's are usually about 60. But this one here is very acidic, as we'll discuss in a moment, with a pK of around 15. The next example is cycloheptatriene, which is this compound shown here. These hydrogens on an sp3 carbon, if we were to remove one of them with base, we would leave behind a lone pair with a negative charge. That means that if we count those 2 electrons, we're going to have a total of 8 pi electrons in this ring. So 6 from the double bonds, another 2 from this one. So this anion would be predicted to be anti-aromatic if it's a flat structure. The other possibility would be if we lose a hydride, so an H minus, meaning a hydrogen with a lone pair, leaving behind a carbocation. That creates a cycloheptatrienyl cation. It has an empty p orbital, so there's no pi electrons on this carbon. There are 6 from the double bonds for a total of 6 pi electrons. Because of the p orbital on this carbon, you can complete the cyclic pi cloud, and because there's only 6 pi electrons, this compound will be predicted to be aromatic. The last example is if we lose a hydrogen and leave behind a single electron, unpaired electron. In other words, we create a radical as shown here, that lone pair would be counted as in the number of pi electrons. So there would be a total of 7 pi electrons, which would make this compound non-aromatic. So neither aromatic or anti-aromatic due to the odd number of electrons. Cyclopentadiene is a compound that is a hydrocarbon, and unlike most hydrocarbons, this is a very acidic compound. Most hydrocarbons have a pKa of somewhere around 60. This compound, however, is highly acidic with a pKa of about 15 or 16. If we add sodium hydroxide, which is a base, it will remove one of these protons, resulting in an anion. And because this anion is aromatic, it means it is very, unlike most anions, is very stable and very likely to form. And so the hydrocarbon that we started with is highly acidic because it wants to form this highly stable anion. The compound that we're producing, the anion, is aromatic because we have 4 pi electrons from the double bonds and another 2 from this lone pair that can be placed in a p orbital to complete this pi cloud, and therefore is going to be counted in the number of pi electrons. So you can see this diagram, orbital diagram, with a p orbital at every carbon, and then there's 4 carbons that have a single electron. Those are the carbons that have the double bonds, so there's a p orbital at each one, and there's an electron in each p orbital. And there is 1 carbon, this one, which is shown here, which has another p orbital as well with a lone pair. That allows an uninterrupted pi cloud, and then there are a total of 6 pi electrons within that pi cloud. The hydrogen that is shown here in this carbon with the lone pair is going to be in the same plane as the ring and sort of out of the way of the pi cloud. 1,3,5-cycloheptatriene is a compound that likes to form a cation by losing a hydride. So one of the ways it could do that is by reacting with Br2. So Br2 would result in abstracting a hydrogen and the lone pairs on that hydrogen to produce HBr. And more importantly, leaves behind a carbocation on this carbon. So it produces a cycloheptatrienyl cation. This cation, unlike most cations, is very stable because it is an aromatic cation. There are 6 pi electrons from the double bonds that we have in this molecule, and there is an empty p orbital on this carbon, which allows an uninterrupted pi cloud. Since there's no electrons on that carbon, we don't add any more to the count, so there's only 6 pi electrons overall in this pi cloud. Here's a look at the orbital diagram. So every one of the carbons with the double bonds have a p orbital with a single electron, which you can see in this diagram. And there is a 7th carbon, which is where the carbocation is, which has a p orbital, and it is empty. In other words, there's no electrons. That empty p orbital allows the pi cloud to continue around the ring, and there's only a total of 6 pi electrons. So overall, this compound, this cation, is aromatic. In this question, we have an example of applying the aromaticity rules towards a reaction product. So we have cyclooctatetraene, and the question is asking us why it reacts with potassium metal so readily to produce a dianion. So we want to explain why the reaction happens so quickly or easily, and also determine the geometry of this dianion. Cyclooctatetraene is a compound that has 8 carbons in a ring, and it contains also 4 double bonds as shown here. If we add 2 moles of potassium metal, the metal will add electrons into the ring and form this dianion, which we see here. So the way you could understand this reaction is each carbon of the which has a double bond has an electron, a pi electron within that carbon. And if we add a metal which is capable of donating electrons and becoming a potassium cation, those electrons will be added to one of these carbons, and so we can form a anion at, let's say, 2 of these carbons. Now, what we see here is actually one of several resonance structures we could possibly draw from this dianion. So we could move the lone pair, for example, in this direction, which would force the double bond to move here and create another lone pair. And that can continue around the ring to create other resonance structures. Now, the reason why this reaction happens so readily is because the product is an aromatic compound. So in this product, in this dianion, we have 6 pi electrons from the 3 double bonds we have. And then we have a lone pair which has 2 more electrons here and another lone pair with another 2 electrons. So if we add all of those electrons, we come up with 10 pi electrons for this ring, which would be an example of an aromatic compound, as long as this compound remains flat, and it will in order to become aromatic. And so the product from this reaction is an aromatic dianion, and so it's really stable. That's the reason why the reaction happens so quickly. As far as the geometry of this molecule, I would suspect that each carbon would be trigonoplanar. It would have a p orbital at every carbon to have an uninterrupted pi cloud. Now the bond angles, just because it's an 8-member ring, would be somewhere around 135 degrees, which is the typical bond angles, the internal bond angles for an octagon. A few examples of aromatic heterocycles. Heterocycles are compounds that contain more than one type of atom, so that's one definition, or another way of looking at it, it contains an atom other than carbon within the ring. Heteroatoms generally will have a lone pair or maybe even 2. Those lone pairs can be counted towards the pi or the pi number of electrons if it's beneficial towards the compound. In other words, if it's going to allow the compound to be aromatic. In some cases, we may not count those lone pairs as in the number of pi electrons, since we want to avoid anti-aromaticity. Here's an example of an aromatic compound. It's called pyridine. It looks very similar to benzene, and we have replaced one of the carbons in benzene with a nitrogen. This compound is an aromatic compound. There are 6 pi electrons just from the double bonds, so we do not need to count the lone pair on the nitrogen. And so in total, this compound will have 6 pi electrons, since it's a 6-member ring that has an atom that is sp2 hybridized with a p orbital at every atom in the ring. It's going to be aromatic. Here's how the pi cloud or the orbital diagram looks for this compound. We have a p orbital at every atom in the ring. This is the nitrogen atom here that has a lone pair, shown in green. Each atom within the ring is going to be sp2 hybridized. It's going to have a p orbital. That p orbital will have one single pi electron that allows the double bonds to form. And then on the nitrogen, we have, in addition to that, a lone pair. That lone pair will sit in an sp2 orbital. That sp2 orbital will be in the same plane as the ring itself. And so it's going to be perpendicular to the pi cloud. And so it's out of the way of the pi cloud, and we do not count that lone pair in the number of pi electrons. So there's only 6 pi electrons in total within this ring. Pyrimidine is a compound that again looks similar to benzene or even pyridine. We have 4 carbons and 2 nitrogens within the ring. Each carbon will have a double bond, and there's also a double bond here. So in total, there's 3 double bonds, or in other words, 6 pi electrons for this molecule. The lone pairs on the nitrogens are not needed for this compound to be aromatic. And so as you can see here in green, they're going to be in an sp2 orbital. That sp2 orbital will face away from the pi cloud. So it's going to be in the same plane as the ring, perpendicular to the p orbitals at every atom. And so we do not count those in the pi electrons since they're not part of the pi cloud. There is, however, a p orbital at every atom, including the nitrogens, and that p orbital will have a single electron, which allows the double bonds to form. And so there's a total of 6 pi electrons in this pi cloud, making this compound also aromatic. Let's take a look now at a few examples of 5-member rings and how the aromaticity rules apply to them. First example would be pyrrole, which is this 5-member ring with 4 carbons and a nitrogen. Each carbon contains a double bond, and so there is a p orbital, as you can see by this diagram here. There's a p orbital at every one of these carbons with a single lone pair, which allows those double bonds to form. The nitrogen will be also sp2 hybridized, and it contains a p orbital as well. That p orbital will be in the same plane as the other p orbitals, or will be aligned with the other p orbitals on the carbons. This p orbital on the nitrogen will have a lone pair in that orbital. And so we count those 2 lone pair electrons as part of the pi cloud, giving pyrrole 6 pi electrons. And so this compound is an aromatic compound. Notice that the bond to the hydrogen is formed from an sp2 orbital on the nitrogen overlapping with the 1s orbital on the hydrogen. If we compare this orbital diagram to the ones we saw on the previous slide with pyridine and pyrimidine, which contain nitrogens with lone pair as well, you might recall that in those examples, the lone pairs were on an sp2 orbital away from, or as in the same plane as the ring, in other words, away from the pi cloud. And so in pyridine and pyrimidine, we didn't count the lone pair as part of the pi cloud. In the case of pyrrole, we do need to count the lone pair since it's going to allow pyrrole to become an aromatic compound. So it kind of depends on the situation. Sometimes we count the lone pair as part of the pi cloud since we may need it for that compound to be aromatic. In other cases, we may not count the lone pair. Instead, that lone pair will be in an sp2 orbital away from the pi cloud. Imidazole is a molecule that is also aromatic. It has 2 nitrogens and 3 carbons. If we look at the orbital diagram, each carbon, for example, these 2, will have a p orbital with a single electron, allowing that double bond to form. The nitrogen here and the carbon here labeled with a 2 will each also have a p orbital with a single electron. Now the lone pair on the nitrogen, which is labeled as position 1, it will be held in a p orbital, so we're going to count those 2 electrons, giving this molecule 6 pi electrons. The lone pair on nitrogen 3, however, is actually in an sp2 orbital, which is perpendicular to the other p orbitals, or to the pi cloud. And so that lone pair, which is shown here in green, will not be counted as part of the pi electrons. We saw in this chapter, pyridine, which is the six-member ring with a nitrogen, is an aromatic compound, and the lone pair on the nitrogen is not required for this compound to be aromatic since there are three double bonds. In the case of pyrrole, we also have an aromatic compound, but in this case, the lone pair on the nitrogen is actually required or needed to make this compound aromatic since there's only two double bonds, and so a lone pair would add another two pi electrons, making this compound aromatic. That difference of using the lone pair or not in order to make the compound aromatic or keep it aromatic makes a big difference in how these two amines behave in reactions such as, for example, the reactions that they would undergo with an acid or some electrophile. Pyridine, since the lone pair is not required for aromaticity, tends to be a more basic nitrogen than the one on pyrrole. So when the nitrogen on pyridine reacts with acid, it forms a pyridinium ion, which has a pKa of about 5.2. In the case of pyrrole, this nitrogen lone pair is needed for the compound to be aromatic, and so it has a harder time reacting with acid or even electrophiles in general, since that would mean that we're going to make a bond to either a proton or an electrophile and destroy the lone pair, and we no longer have an aromatic compound when we do that. So the product from a reaction between pyrrole and an acid would be making pyrrolonium, which is shown here. It has a pKa of almost zero, pKa of about 0.4. That means that this compound is more acidic than pyridinium. So that means that this is a weaker base than pyridine. So since this is a weaker acid than pyrrolium, this is a stronger base than pyrrole. That's another way of looking at it. The way we can view this is if we look at the two products from the reactions, we have a pyridinium ion that is still aromatic since we didn't need the lone pair for pyridine to be aromatic. So if we tie it up, the lone pair, we tie it up with a proton bond. It doesn't matter since we still have three double bonds and the product here is still aromatic. In the case of the product from pyrrole, we have to make a bond between the nitrogen lone pair and a proton, destroying the aromatic ring since that lone pair is no longer available to make this product aromatic. And so that's part of the reason why this compound here is less likely to form, which means pyrrole is less basic. Many of the heteroaromatic compounds that we cover in this section are commonly found in molecules that are part of biological systems. For example, many amino acids and nucleic acid bases contain a pyrimidine and an imidazole ring. So here are a few examples. Here is cytosine, thiamine, uracil, which all contain these six-member rings with two nitrogens, which is essentially derivatives of pyrimidine. And then we have in histidine, which is an amino acid, we have an imidazole ring. Oxygen and sulfur atoms sometimes contribute a lone pair in order to make a molecule aromatic. As an example, thiophene contains a sulfur atom plus another four carbon atoms. There are two double bonds, so there are four pi electrons from those double bonds. And so we need a lone pair from the sulfur atom in order to add a couple of more pi electrons and make this compound aromatic. And so if we look at the orbital picture of this molecule, we have four carbon atoms, each with a p orbital containing a single electron, which is what leads to the double bonds in the molecule. And then we have the sulfur atom with two lone pairs. One of those lone pairs will sit in a p orbital that will allow this compound to be aromatic. So those two electrons will be part of the pi cloud. So thiophene has 6 pi electrons and therefore is an aromatic compound. Note that the other lone pair will be inside of an sp2 orbital, and it will be on the plane of the ring. In other words, it will be away from the pi cloud, and so it doesn't add to the total pi electron count. Boron is an atom that in most compounds, it will have 3 bonds coming from it, so it will be trivalent. And in such compounds, boron generally acts like a carbocation in that it contains a p orbital that has 0 electrons in it. And so that p orbital will allow the pi system to continue, involving a compound that is close to being aromatic. However, the p orbital will not have any electrons, and so we don't count any electrons from the boron. An example is borosine, which has 3 nitrogen atoms and 3 boron atoms. The boron atoms are sp2 hybridized, and they will have 0 electrons from the p orbital. These nitrogen atoms, at least in borosine, will be also sp2 hybridized, and the lone pair will be counted in the pi electrons of this compound. And so this particular resonance form has 6 pi electrons and is therefore aromatic. There's another resonance form of borosine that we see here that has partial or has double bonds as well as single bonds. So we can get to that resonance form by using a lone pair, for example, to go in this direction to make a double bond this way. And then this nitrogen will contribute a lone pair into the empty p orbital of the boron to the right of it to make a double bond in that direction. And then this nitrogen atom will contribute a lone pair to make a double bond between the nitrogen and boron. And so we get to this resonance structure that not only has these alternating double and single bonds, but it also has charges. So the nitrogen, because it gave up a lone pair to make the double bond, will have a positive charge. And then the boron, because it is gaining electrons in that double bond, will have now a negative charge, at least a negative formal charge. This resonance structure will also be aromatic, and the way you can count the pi electrons is just simply from the double bonds. So there are 3 double bonds, and so there will be 6 pi electrons. In this question, we're going to look at furan, which is the structure here. It contains 4 carbon atoms and an oxygen atom. Notice that furan is very similar to thiophene. And so we want to show how this compound is aromatic, just like thiophene. Furan is a compound that is similar to both thiophene and pherol in that it contains 4 carbon atoms and a heteroatom. In the case of furan, we have an oxygen atom that has 2 lone pairs. And because there are 2 double bonds in this molecule, that means that furan has 4 pi electrons just from the double bonds. And so we need to use one of the lone pairs on the oxygen in order to make this compound aromatic with 6 pi electrons. And so the orbital picture of furan looks like this, where we have a p orbital at every atom in the ring. The carbon atoms will have a single electron in each p orbital. The oxygen will have a p orbital with 2 electrons, which is one of the lone pairs on the oxygen atom. The other lone pair will sit in an sp2 orbital, and that sp2 orbital will be in the same plane as the ring or perpendicular to the pi cloud. In this section, we're going to cover some examples of aromatic polycycles. These are compounds that contain multiple rings, and they are also aromatic. An example is naphthalene, which is essentially 2 fused benzene rings together. As you see by the structure, we have 5 double bonds, and therefore we have 10 pi electrons. Notice that the double bonds are also alternating. And so when we look at the orbital diagram of this compound, in particular the p orbitals, there's a p orbital at every carbon atom in the ring, and every one of these p orbitals contains a single electron that allows those double bonds to form. And so overall, this structure is very planar. It's obviously cyclic, and it contains an uninterrupted pi cloud. And because it has 10 pi electrons, naphthalene is an aromatic compound. Note that naphthalene has 3 resonance forms, which you can see here. So starting with this structure, we can move the double bonds clockwise. So this double bond moves this way, this one that way, and so on. So we get to this other resonance form. Notice that the double bond here in the middle is shown on the right side, but we could easily have shown it on the left ring. Another resonance form can be shown by moving the electrons on the right or the ring on the right side of the molecule, as shown here, to give us this other resonance form. All 3 resonance forms are aromatic. Another related example is anthracene. It contains essentially 3 fused benzene rings. If we count the double bonds, we have 7 of them. That means this molecule has 14 pi electrons, and because it has an uninterrupted pi cloud, we have an aromatic compound. Many polycyclic aromatic compounds, such as benzopyrene, are compounds that are considered carcinogenic. The reason for that is, for example, in the case of benzopyrene, it is metabolized in the body by several oxidation reactions that add epoxides as well as alcohols. And so we produce intermediates such as this one here that are able to react with different nucleophiles in the body, such as DNA, that eventually leads to the misinterpretation of DNA during replication and therefore leading to cancerous cells. Other polycyclic aromatic compounds are also carcinogenic because of their flat structure. They're able to also slip in between DNA bases within the DNA molecules, which leads to errors in replicating the molecule, since essentially it leads to a kink in the structure while replication occurs. A physician named Percival Pott recognized many centuries ago that certain occupations like chimney sweepers led to an increase of certain types of cancers. It is now known that, at least in the case of chimney sweepers, this is due to the exposure to benzopyrene and other polycyclic aromatic compounds. In this section, we'll cover some examples of aromatic polycyclic heterocycles. These are compounds that contain both a heterocycle and, of course, multiple rings. One example is quinoline, which contains a pyridine attached to a benzene ring. This compound contains 5 double bonds, and so it has 10 pi electrons. The lone pair on the nitrogen is not needed in order to make this compound aromatic, and so that lone pair will be found in an sp2 orbital. Isoquinoline, which is shown here, has also 10 pi electrons. It is due to the fact that the molecule has 5 double bonds, and again, the lone pair on the nitrogen is not needed for this compound to be aromatic, so it sits in an sp2 orbital. Indole is a benzene ring fused together with a pyrrole ring. There are 4 double bonds, giving us 8 pi electrons. So the lone pair on the nitrogen will be used in this case in order to give this compound 10 pi electrons. the lone pair will typically be in a p orbital in order to be part of the pi cloud. Purine, which has 4 nitrogen atoms, has 8 double bonds, so that's 4 double bonds and 8 pi electrons from those double bonds. And so we're going to use the lone pair on nitrogen labeled at position 9 in order to add another 2 pi electrons and make this compound aromatic with a total of 10 pi electrons. Many examples of biological molecules that contain an aromatic polycyclic heterocycle. Here's just a few examples. Tryptophan, which is an amino acid, contains an indole ring. Adenine and guanine, which are, of course, DNA and RNA nucleic acid bases, both contain a purine ring, which you can see here. And then lastly, quinine, which is a potent antimalarial agent, contains a quinoline ring, as shown here. Acetylene, which is this beautifully blue-colored hydrocarbon, which is also an isomer of naphthalene, has a 7-member ring fused together with a 5-member ring. Based on this structure, try to determine whether this compound is aromatic or not, and then try to draw another resonance form of this compound. Based on the structure of acetylene, which has 5 double bonds, and the fact that it has alternating double and single bonds, leads us to believe that this compound should be aromatic. So there's a total of 10 pi electrons. Every carbon atom has a p orbital. Since it's part of a double bond, it must be sp2 hybridized, and therefore it must have a p orbital. And so that allows this compound to be aromatic by the fact that it has 10 pi electrons and it has a uninterrupted cyclic pi cloud. A second resonance structure of acetylene is shown here on the right. We can get to that by moving the electrons from the double bonds in this direction. For example, we can move this double bond this way, this one here, this one here, this one here, and this one here. As we saw earlier in this chapter, one of the rules that aromatic compounds must obey is the Huckel rule, which says a compound must have 4n plus 2 pi number of electrons in order to be aromatic. So where does this rule come from? One way of explaining it is based on molecular orbital theory, and we're going to use the example of benzene and look at its molecular orbital diagram in order to understand the Huckel rule. If we focus solely on how the pi bonds are formed in benzene, we'll have this simplified molecular orbital diagram for benzene. Now, if we include all of the sigma bonds, the molecular orbital diagram becomes way more complicated than we can cover at this level. So we're only going to look at how the pi bonds are formed, which are formed by taking 6 p orbitals, 1 from each carbon atom. And if we fuse them together, we'll come up with 6 new molecular orbitals, which belong not to the original carbon atoms, but now to the entire molecule. 3 of those molecular orbitals will be lower in energy than the original 6 p orbitals. And so you can see that they are below in terms of energy. In other words, they're more stable than the original p orbitals. 3 of the orbitals will also be higher in energy, and so these are considered anti-bonding orbitals. The energy of each of these orbitals increases as we go up, and the lowest energy orbital would look something like this, where the 6 p orbitals are completely aligned, where the same faces are facing in the same direction. So that's illustrated here in a simple way by using six red colored lobes facing on the top of the molecule, and then six blue ones on the bottom. If we introduce a node, in other words, where the faces of these lobes change, so in this orbital, the one on the left, I guess, it changes in going from this orbital to this one here. So there's a phase change there, and there is a node or a place where electrons don't go, basically. And on the other side of the ring, there's again a node. So this molecule actually has a node that traverses the entire molecule. And so because of that node, this molecule or this orbital is higher in energy than the one we have here. There's another example of a molecular orbital that also has a node, now this time going this way, and it cuts across the two p orbitals on this atom on the left and this atom on the right. That's why those lobes are not shown, because there's a node there. And then there are two other orbitals on this side of the molecule which are aligned, and then two other ones on this side which are aligned. As we go up, we're going to encounter more and more nodes. So there's actually two nodes on this molecular orbital, one going this way, one going this way. And on this one, there's a node here, and there's a node here. And then on the last one, there's actually three nodes. And so this is the highest energy molecular orbital. Benzene has not only 6 atomic orbitals to begin with that eventually turn into 6 molecular orbitals, but it also has 6 pi electrons. So once you build the molecular orbital, if we start to add the electrons that we have to work with, which are 6 electrons, 1 at each p orbital, that now when it comes to the molecular orbital will be placed as follows. So 2 will go in the lowest molecular orbital, which is here. So two electrons go there. The next 2 will go like this. One will go on the orbit on the left, the other one on the right, since these two orbitals are equal in energy. In other words, they're degenerate orbitals. Since we have 2 more electrons, we're going to completely fill this orbital, and then we're also going to completely fill this orbital. And that gives us 6 pi electrons, which completely filled the 3 bonding molecular orbitals. Notice we don't have any more electrons to put into the anti-bonding orbitals. As a result of going from 6p orbitals into 6 molecular orbitals, and only filling the 3 lowest molecular orbitals in energy, which happen to be lower in energy than the original p orbitals, we're essentially, in making benzene, making the molecule more stable. All right, so this partially explains why having a benzene molecule is more stable than just having these individual atoms, carbon atoms, separate. We essentially create a molecule that has molecular orbitals that are more stable than the original p orbitals. This is something that's going to happen with every aromatic compound. If we draw the molecular orbital diagram, we're always going to place the pi electrons into only bonding orbitals, and we're always going to fill them completely. And we're never going to put any electrons into the anti-orbitals. That's not what we see, however, with anti-aromatic compounds. Let's review some of the key points that we learned from looking at the molecular orbital diagram of benzene. One of the things that we saw was that bonding molecular orbitals are more stable than atomic orbitals. And of course, they're also more stable than anti-bonding molecular orbitals. Anti-bonding molecular orbitals, on the other hand, tend to be less stable than atomic orbitals. When I mention atomic orbitals, I'm referring to the p orbitals from which both the bonding molecular orbitals and the anti-molecular orbitals are formed from. As we start to fill in the molecular orbitals, we generally start with the most stable molecular orbitals, which are those at the bottom of the molecular orbital diagram. We start to fill them one electron at a time. And so each molecular orbital will get two electrons. Once we use up both electrons, we will move on to the next most stable molecular orbital diagram. If we run into a molecular orbital diagram that is degenerate, in other words, it has the same energy, then we have to fill each degenerate orbital one electron at a time. And then once each degenerate orbital is filled with a single electron, we go back to adding a second electron into each of these degenerate orbitals. This is based on Hund's rule. Note that we use this rule in filling atomic orbitals as well. So if you notice, the molecular orbital diagram of benzene has 6p orbitals. Each one has an electron, rather than having 3 that are completely filled and having 3 that are completely empty. As we saw, benzene has 3 bonding molecular orbitals that are completely filled. And so since these molecular orbitals are lower in energy than the original atomic orbital, benzene is more stable due to these filled molecular orbitals that are bonding. In other aromatic compounds, we're going to find the same situation where all of the bonding molecular orbitals will be filled. Looked at the molecular orbital diagram of benzene, we really didn't discuss how you can draw or come up with a molecular orbital diagram in the first place. It turns out that it's quite complicated, and for even simple molecules like benzene, generally we have to use computer models that will predict what the molecular orbital diagram will look like. However, there is a method called the frost circle method that actually allows us to predict what a molecular orbital diagram will look like for simple compounds like benzene and others. This method is as follows. It starts with drawing the ring of whatever aromatic compound we have with one of its corners down. So you can see here for benzene, one of the corners of the benzene ring is pointing down. That would be as opposed to drawing one of the flat sides down. So this is another way we could potentially draw benzene, and obviously we don't want to do this since instead of a corner we have one of the flat sides of the ring down. After you draw a ring like this, we want to draw the molecular orbital diagram by drawing an orbital at each atom within the ring. So we start with this carbon that is down here. We draw a molecular orbital there. Then we have 2 more carbons above that. So we draw 2 more orbitals. Then we have 2 more carbons. So we draw 2 more molecular orbitals. And then lastly, we have 1 last carbon at the top. And so we draw a molecular orbital there. Once we have the molecular orbital diagram, we're going to label the orbitals based on their location according to the midpoint of the molecule. So if we draw the midpoint of the molecule, it cuts across this way. And anything below that midpoint is considered a bonding molecular orbital. So that would be these 3 molecular orbitals. The 3 above that midpoint are considered anti-bonding molecular orbitals. And if we happen to have any molecular orbitals in the middle or right at the midpoint, then those are considered non-bonding molecular orbitals. We lastly start to fill electrons from the lowest molecular orbital. So we start here adding 2 electrons. Then we come across 2 degenerate orbitals. So we place an electron here, 1 more electron here. And then since we have 2 left, we go back to this one and we add a second one on this molecular orbital. We have used up all 6 pi electrons that we started with. Remember, benzene has 6 pi electrons because of the 3 double bonds. Those are the only electrons we care about when it comes to the frost circle method. And then last thing we want to determine is whether this compound is aromatic or not based on the frost circle method. If all of the molecular orbitals that are bonding are filled, then this would be predicted to be an aromatic compound. If we have partially filled bonding orbitals, or we start to add electrons to the anti-bonding orbitals, then we will not have an aromatic compound. Let's look at a few examples involving the frost circle method of potentially aromatic compounds. So starting with the cyclopentadienyl cation, which has 4 pi electrons. This is the structure. You can see it has 2 pi bonds, so 4 pi electrons. We also have a carbon with an empty p orbital. That's where there's a carbocation. And so there's 0 electrons there, but it does allow the pi cloud to be completed. If we place one of the corners of this ring facing down, we can draw a molecular orbital there. And then we have come across 2 carbons above that, so we add 2 more orbitals. And then lastly, there's 2 more carbons on the top here, so we add 2 more molecular orbitals there. We only have 4 pi electrons, so if we start to fill from the bottom, the most stable molecular orbital, we place 2 electrons there. And then we place one here, and we have ran out of electrons. So notice this compound does not have completely filled bonding molecular orbitals. So the cyclopentadienyl cation is predicted not to be aromatic. As we know from what we learned earlier this chapter, cyclopentadienyl cation is actually anti-aromatic. And it's a very stable compound. It's actually a diradical with 2 unpaired electrons. Cyclobutadiene, which has this structure here, has 4 pi electrons due to the 2 pi bonds. And if we draw one of the corners down, we can draw a molecular orbital diagram from that. So if we add a orbital here, add 2 more here where the midpoint is, making those 2 orbitals non-bonding. And then lastly, we have one more orbital at the top, and that one is anti-bonding. The one down here is bonding. We have 4 pi electrons, so we fill the bottom orbital, and then we have 2 more, so we put one here and one here since these are degenerate orbitals. This compound has partially filled molecular orbitals, so it is not going to be aromatic. In fact, it's predicted to be anti-aromatic, as we learned earlier in this chapter. One last point that I forgot to mention is that notice that these 2 molecular orbitals are actually slightly below the midpoint of this molecule. So if we really draw this ring to scale, the midpoint is just slightly above those 2 carbons, and making these 2 orbitals bonding rather than being at the midpoint where they would be non-bonding like these 2 molecular orbitals. There are 2 well-known examples of carbon-based polymers, which are known as graphite and diamond. Graphite is an infinite network of aromatic polymer sheets of benzenes. So the network has multiple benzene rings that are fused together, and then these sheets will be held together through nonpolar interactions. Diamond, on the other hand, is made up of sp3 carbons that are bonded together. So it is not an aromatic network. And then a third form of carbon was discovered about 1986 called buckyballs. They look like this, essentially a soccer ball. Over the years, several sizes have been discovered. This one here is involving 60 carbons. Buckyballs, despite having only sp2 hybridized carbons are not really aromatic compounds. The reason for that is due to the non-flat structure that these rings have. So it is completely made up of hexagons as well as pentagons. But despite this, due to the curvature of the molecule overall, the p orbitals and the pi cloud are not able to fully interact, and so that leads to this compound being non-aromatic. Buckyballs are named after an architect that popularized these geodome structures back in the 1950s and 60s. Now, note that buckyballs have been studied since their discovery for many applications, including as a drug delivery system that involves placing drugs inside of the buckyball and then having some sort of attachment on the outside of the buckyball that delivers the drug to a delivery target within the body. Those that worked on the discovery of buckyballs and their applications won the Nobel Prize in Chemistry in 1996.